How do soda plants keep millions of bottles tasting identical across cities and continents? One small shift in syrup ratio or water chemistry can turn a perfect pour into something instantly wrong. In this video, we follow Dr. Pepper, Sprite, and Canada Dry from concentrate to capped bottles, uncovering the hidden checkpoints that keep every sip unmistakable. Dr. Pepper is manufactured by preparing a concentrated flavor syrup, blending it with treated water at a precise ratio, carbonating the finished beverage to a fixed dissolved CO2 level, then filling and sealing containers under conditions that prevent loss of carbonation and flavor. Production starts with water because it is the largest component and it sets the baseline for taste and carbonation behavior. Incoming water is filtered to remove suspended solids and then polished through fine filtration to tighten clarity. Mineral content is adjusted to a target profile because hardness and alkalinity change how acidity and flavors present. The water is then cooled because colder liquid absorbs CO2 more efficiently and gives more stable carbonation control. While water is being prepared, a sweetener stream is built. Depending on the formula, this can be a sugar syrup or a sweetener solution that behaves like syrup in dosing. Granulated sugar is dissolved in heated tanks with agitation until the solution is clear. The syrup is filtered to remove undissolved crystals that could seed crystallization later. Syrup concentration is monitored by density, so every batch has the same sweetness potential per liter. A separate flavor concentrate is prepared as a high-strength blend that will later be diluted. Flavor components are staged in small tanks and metered by weight into a blending vessel. Many flavor components are carried in alcohol or in emulsified oils, so they stay stable in water. High shear mixing is used to disperse oil-based components into a uniform emulsion that will not separate during storage. The concentrate is filtered to remove any particulate and to protect dosing valves. Acid addition is managed early in the syrup phase because acidity affects microbial stability and also changes flavor perception. Acid is prepared as a liquid solution for accurate metering. It is injected into the syrup or into the flavor concentrate depending on the line design. pH is measured and adjusted to a tight set point because small shifts change the balance between sweet and sharp notes. Buffer salts can be used in very small amounts to stabilize pH drift. If the product uses caramel color, it is handled as its own dosing stream. Caramel color is stored in tanks with gentle mixing because it can stratify. It is metered into the syrup blend at a controlled rate. Inline color measurement can be used to confirm shade stability across the run. Color is stabilized by keeping oxygen pickup low and by avoiding excessive heat exposure. Once sweetener, flavor, acid, and color are prepared, they are combined into a finished syrup. This syrup is the concentrated recipe that will be proportioned into final beverage. The syrup is mixed in a tank with controlled agitation that avoids foaming. Foaming traps air and later interferes with carbonation. The finished syrup is held at a controlled temperature and then delivered to the blending system through metered pumps. Final beverage blending is commonly done with a proportioning blender. The blender meters syrup and treated water by mass flow or by volumetric flow with density compensation. The ratio is the key control point because it determines sweetness and flavor intensity. Ratio control is verified by measuring soluble solids in the blended stream and comparing it to a target. When the ratio drifts, the control valves adjust in real time. Before carbonation, the blended beverage is typically deaerated. Deaeration removes dissolved oxygen and trapped air. Oxygen dulls flavor over time and also reduces carbonation efficiency. Deaeration is done under vacuum, where the liquid spreads as a thin film. Vacuum pulls gas out and the liquid leaves with lower oxygen content. The beverage is kept cold during this step to preserve volatile flavor notes. Carbonation follows deaeration. and it is controlled by temperature, pressure, and contact efficiency. CO2 supply is filtered and regulated to a stable pressure. The beverage enters a carbonator, where CO2 is injected and dissolved under pressure. The carbonator can use a packed column or a sintered stone system that creates fine bubbles. Fine bubbles create high surface area and improve dissolution. Pressure is held high enough to drive CO2 into solution and to prevent breakout. Dissolved CO2 level is monitored continuously. The measurement can be inferred from temperature and pressure or measured directly with inline instruments. The line targets a defined carbonation volume that matches the intended bite. If temperature rises, CO2 solubility drops and the instrument will show a fall in dissolved gas. The system compensates by raising pressure or by improving cooling. Stable cooling is therefore central to carbonation consistency. Once carbonated, the beverage must be handled gently. High shear pumps can cause CO2 to break out and create foam. The line therefore uses low shear pumps and smooth piping with gradual bends. The product is kept under pressure all the way to the filler. Pressure maintenance prevents carbonation loss and also prevents foaming at the fill valve. Container preparation runs in parallel with beverage preparation. For cans, the empty cans are conveyed and cleaned with air and rinsing systems. For bottles, the containers are oriented and presented to the filler. Plastic bottles may be produced nearby by blow molding and then transferred quickly. Glass bottles arrive as formed containers and are staged for feeding. All containers are timed, so the filler receives a continuous flow without gaps. Filling is done on counter-pressure equipment for carbonated beverages. In a counter-pressure filler, the container is first pressurized with CO2 to match the bowl pressure. This reduces foaming during liquid entry. A fill valve then opens and beverage flows in with controlled velocity. Fill height is controlled by a level probe or by timed volumetric control. Once filled, the valve closes and pressure is released in a controlled way so the liquid does not erupt. Foam control at the filler is managed by temperature and valve design. Cold liquid reduces foam because gas stays dissolved. Smooth valve surfaces reduce nucleation points where bubbles form. Fill tubes can deliver liquid down the side of the container to reduce turbulence. Turbulence increases foam and can cause underfills. The filler, therefore, balances speed with smooth flow. After filling, the container is sealed immediately. Cans are sealed by seaming, where a lid is placed and rolled into a tight seam. Seam geometry is controlled by roller, profiles, and force. Seam integrity is critical because a tiny leak will release CO2 and flatten the product. Bottles are capped with controlled torque. Torque control ensures the seal is tight without damaging threads. Headspace management is part of carbonation retention. A defined headspace volume is left above the liquid. This headspace contains CO2, which will equilibrate with the dissolved CO2. If headspace is too large, carbonation can be lower at equilibrium. If headspace is too small, fill accuracy becomes difficult and overflow increases. Many lines use a CO2 jet just before capping to displace air in the headspace. This reduces oxygen and improves flavor stability. Once sealed containers move to coding and inspection. Date codes are printed by inkjet or laser systems. Inspection checks can verify fill level and cap presence and seam quality. Seam inspection on cans can include thickness checks and overlap checks. Leaker detectors can find micro leaks by pressure decay or vacuum methods. Out-of-tolerance units are rejected automatically. If the line produces multi-pack products, the sealed units are collated next. Cans can be wrapped in film or placed in cartons. Bottles can be grouped into shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heat is controlled so the film shrinks without overheating the product. Cartons are erected and loaded with gating systems that maintain alignment. Case packing follows. Packs are arranged into cases with patterns that protect seams and caps. Cases are sealed and labeled. Palletizing stacks, cases to minimize movement and to keep load stable. The product is then stored and distributed with temperature control practices that reduce carbonation drift. Sprite is manufactured by preparing a citrus flavor syrup, blending it with treated water at a fixed ratio, carbonating the beverage to a precise dissolved CO2 level, then filling and sealing containers under counter. Pressure, so carbonation and aroma stay stable. Production starts with water because water chemistry controls acidity perception and carbonation behavior. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target hardness and alkalinity so the final drink has consistent bite. Water is then cooled because colder water holds CO2 more efficiently and reduces foaming during filling. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup is clear. Syrup concentration is measured by density and held in a narrow band because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could seed crystallization or clog valves. For other sweetener systems, a concentrated solution is prepared and handled as a metered liquid feed with consistent density. The citrus flavor system is built as a concentrate that can be dosed precisely. Lemon and lime flavor components often include oil-based fractions that must be emulsified to remain stable in water. The flavor concentrate is mixed in a blending tank where carriers and emulsifiers are combined with flavor oils. High shear mixing reduces oil droplet size and stabilizes the emulsion. Droplet size control prevents separation and reduces ring formation at the surface of the final beverage. The concentrate is filtered to remove any particulate and to protect dosing pumps. Acid addition is managed as part of syrup formulation because pH defines freshness and also affects how sweetener is perceived. Acid is prepared as a liquid solution for accurate dosing. It is injected into the syrup or into the flavor concentrate depending on process layout. pH is measured and adjusted to a tight set point. Small changes in pH shift the balance between sharp citrus and sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main control is acid dose. If the formulation includes a clouding system to support the citrus profile, it is prepared as an emulsion stream. Cloud systems are designed to keep a slight visual opalescence and to carry flavor. They are mixed under shear and then held with gentle agitation so they do not cream. Stability is verified by checking droplet size and separation rate. Once sweetener syrup, flavor concentrate, acid, and any cloud system are ready, they are combined into a finished syrup. The syrup is mixed with controlled agitation that avoids foaming. The syrup is then held at a stable temperature and delivered to the proportioning blender through metered pumps. Filters at this stage protect the blender and carbonator from particles and gel lumps. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. The ratio is controlled by mass flow meters or by volumetric meters with density compensation. Ratio accuracy is the main determinant of consistent taste. The blended stream is monitored by inline soluble solids measurement. When solids drift, the control system adjusts valve positions to correct the syrup-water ratio. Before carbonation, the blended beverage is commonly deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen dulls citrus aroma over time and increases oxidation in flavor components. Air also reduces carbonation efficiency because it occupies headspace in the carbonator and promotes foam. Deaeration is performed under vacuum where the beverage spreads as a thin film. Vacuum pulls gases out and the liquid leaves with lower oxygen content. Carbonation follows, and it is controlled by temperature, pressure, and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator, where CO2 is injected and dissolved under pressure. Many carbonators use a sintered stone or injector that forms fine bubbles. Fine bubbles create high surface area and dissolve quickly. The carbonator maintains a pressure high enough to keep CO2 in solution and prevent breakout. Dissolved CO2 level is monitored continuously. Instruments measure or infer carbonation based on temperature and pressure. The line targets a defined carbonation level that gives a crisp bite. If temperature rises, CO2 solubility drops and gas begins to break out. The system compensates by increasing pressure or improving cooling. Tight temperature control in the blending and carbonator sections therefore supports stable carbonation. Once carbonated, the beverage must be handled with low turbulence. High shear pumps and sharp piping bends can release CO2 and create foam. The line uses low shear pumps and smooth piping layouts. The product is kept under pressure all the way to the filler bowl. Pressure maintenance prevents CO2 loss and reduces foaming at the fill valve. Container handling runs in parallel with beverage. Preparation. Cans or bottles are conveyed, oriented, and cleaned. Cans are often rinsed and drained before filling. Bottles are oriented and may be rinsed or air-blown to remove dust. Plastic bottles may be supplied from blow molding and then transferred to the filler quickly. Container temperature can influence fill behavior because warm containers promote foaming. Lines manage container staging to avoid excessive warming. Filling is performed on counter-pressure fillers. The container is first sealed to the fill valve and pressurized with CO2 to match filler bowl pressure. This equalization reduces foaming when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a probe or by timed flow depending on equipment design. Controlled flow reduces turbulence and helps maintain carbonation. After the container reaches fill level, the valve closes and pressure is released in a controlled way. Controlled release prevents the liquid from erupting and prevents excessive foam that could contaminate the seal. For cans, the lid is applied and the can is seamed immediately. For bottles, the cap is applied immediately with controlled torque. Rapid sealing locks carbonation and reduces oxygen pickup. Headspace control is part of maintaining carbonation and flavor. The fill is set to leave a defined headspace volume. Many lines apply a CO2 jet just before capping or seaming. This displaces air from the headspace and reduces oxygen content. Reduced oxygen protects citrus aroma and reduces flavor drift. Headspace CO2 also supports equilibrium carbonation by providing a gas reservoir above the liquid. After sealing containers, move to inspection. Fill level inspection checks for underfills and overfills. Cap inspection checks for missing caps and skewed caps. Seam inspection checks seam thickness and overlap on cans. Leak detection can identify micro leaks that would cause carbonation loss. Out of specification units are rejected automatically. If the product is packed into multi-packs, the sealed units are collated next. Cans can be wrapped in film or placed in cartons. Bottles can be grouped in shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heating is controlled so it shrinks film without overheating the beverage. Cartoning systems erect cartons and load units with gating systems that maintain spacing. Canada Dry Ginger Ale is manufactured by preparing a ginger citrus flavor syrup, blending it with treated chilled water at a fixed ratio, carbonating the beverage to a controlled dissolved CO2 level, then filling and sealing containers under counter pressure so carbonation and aroma remain stable. Production starts with water because it defines the baseline taste and the way carbonation behaves. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target profile because hardness and alkalinity change perceived sharpness and sweetness. Water is then cooled because colder liquid absorbs CO more efficiently and reduces foaming at the filler. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup becomes clear. Syrup concentration is monitored by density because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could clog valves and create settling. For alternative sweetener systems, a concentrated sweetener solution is prepared and handled as a metered liquid feed with stable density. The ginger flavor system is built as a concentrate that can be dosed precisely. Ginger character often includes both water-soluble notes and oil-based notes that need controlled dispersion. Flavor components are staged in small tanks and metered by weight into a blending vessel. Oil-based fractions are emulsified so they remain stable in the final beverage and do not separate in storage. High shear mixing reduces oil droplet size and improves emulsion stability. The concentrate is filtered to remove any particulate that could seed haze or block nozzles. Acid addition is managed as part of syrup formulation because pH controls brightness and stability. Acid is prepared as a liquid solution for accurate metering. It is injected into the syrup blend or into the flavor concentrate depending on line design. pH is measured and trimmed to a tight set point because small shifts change the ginger bite and the perceived sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main lever is acid dose. If the formula uses a color system or a cloud system, those are handled as separate dosing streams. Color is held in tanks with gentle mixing and metered into the syrup at a controlled rate. Cloud systems are prepared as emulsions that remain suspended and carry aroma. Cloud emulsion. Stability is controlled by droplet size and by the choice of emulsifier. These streams are filtered and then injected into the syrup blend under controlled mixing. Once sweetener syrup and flavor concentrate and acid and any supporting streams are ready, they are combined into a finished syrup. Mixing is designed to create uniformity without entraining air. Air entrainment creates foam and reduces carbonation efficiency later. The finished syrup is held at a stable temperature to keep viscosity consistent for metering. It is delivered to the proportioning blender through metered pumps and protected by final inline filters. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. Control can be mass flow based or volumetric with density compensation. Ratio accuracy is the main determinant of consistent taste from run to run. The blended stream is monitored by inline soluble solids measurement as a proxy for syrup ratio. When solids drift, the control system adjusts valves to correct the ratio in real time. Before carbonation, the blended beverage is typically deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen can dull delicate ginger notes over time and can change aroma character during storage. Air also interferes with carbonation by promoting foam and reducing CO2 dissolution efficiency. Deaeration is performed under vacuum, where the liquid spreads as a thin film. Vacuum pulls gases out and the liquid exits with lower oxygen content. Carbonation follows deaeration and is controlled by temperature and pressure and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator where CO2 is injected under pressure. Injection often uses a sintered stone or fine bubble injector to create small bubbles with high surface area. High surface area improves dissolution speed and reduces large bubble breakout. the carbonator maintains pressure high, enough to keep CO2 in solution. Dissolved CO2 is monitored continuously by instrumentation or by calculation from pressure and temperature. Temperature is a critical variable because CO2 solubility drops as temperature rises. The system compensates for temperature drift by adjusting pressure and by tightening cooling upstream. Stable chilling of water and blended beverage is therefore essential for consistent carbonation. Once carbonated, the beverage must be transported with minimal turbulence. Turbulence releases CO2 and creates foam, which leads to fill problems and carbonation loss. The line uses low shear pumps and smooth piping layouts. Sharp bends and sudden diameter changes are avoided. The product remains under pressure from carbonator through filler bowl to keep gas dissolved. Container handling runs in parallel with beverage preparation. Cans or bottles are conveyed and oriented and cleaned. Cans are typically rinsed and drained before entering the filler. Bottles are oriented and can be air rinsed or lightly rinsed, depending on line design. Plastic bottles may be supplied from blow molding and transferred quickly to avoid dust pickup. Container temperature matters because warm containers promote foaming. Staging is designed so containers do not heat excessively before filling. Filling uses counter-pressure equipment designed for carbonated beverages. Each container seals to a fill valve and is pressurized with CO2 to match the filler bowl pressure. Pressure equalization reduces turbulence when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a level probe or by timed flow depending on the filler type. Smooth flow is critical because foaming can cause underfills and messy seals. After the target fill level is reached, the valve closes and pressure is released in a controlled way. Controlled release prevents eruption and reduces foam at the top. Cans are then lidded and seamed immediately. Seam rollers form a tight double seam that locks the lid to the can body. Seam geometry is controlled by roller profiles and force because seam, overlap, and tightness determine leak resistance. Bottles are capped immediately with controlled torque. Torque control ensures sealing without damaging threads or liners. Headspace control supports carbonation retention and aroma stability. A defined headspace volume is left above the liquid. Many lines apply a CO2 jet just before sealing. This displaces air in the headspace and reduces oxygen pickup. Reduced oxygen helps keep the ginger aroma crisp during storage. Headspace CO2 also supports equilibrium between dissolved CO2 and gas phase CO2. Immediately after sealing containers, move through inspection. Fill level inspection checks for underfill and overfill. Closure inspection checks for missing caps or misapplied lids. Seam inspection on cans can include overlap checks and thickness checks. Leak detection can identify microleaks by pressure decay or vacuum methods. Out of tolerance units are rejected automatically to protect product consistency. If the product is produced in multiple packaging formats, the downstream handling changes slightly, but the goals remain the same. For multi-packs, cans are collated and wrapped in film or loaded into cartons. Bottles can be arranged into shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heat application is controlled so the film shrinks without overheating the beverage and driving CO2 loss. Cartons are erected and loaded with gating systems that maintain spacing and prevent scuffing. Grape flavor for Fanta is created by combining a concentrated blend of esters and aldehydes in a stainless steel mixing tank. Each flavor compound is pre-measured using peristaltic pumps connected to sealed containers. The mixer runs at low speed to avoid aeration while ensuring even distribution. Glycol-based carriers are added to solubilize the aromatic compounds. Food-grade purple pigment is introduced through a high-shear inline mixer. color density is verified using optical sensors positioned on the outflow pipe. Malic acid is dosed through a diaphragm pump to set target acidity. Potassium citrate is used to buffer pH and stabilize the flavor profile during dilution. The flavored concentrate is transferred to a holding tank through a closed-loop circuit. This circuit is jacketed for temperature stability using chilled glycol at 5 degrees Celsius. Once the concentrate is blended, it waits for combination with sweeteners and water during syrup preparation. In a separate process, sucrose and high fructose corn syrup are stored in heated silos connected to the syrup room. Each is pumped into the blending vessel using independent flow meters. Ratios are defined by weight and adjusted by mass flow controllers. Purified water is added last and enters from a pressure-regulated manifold connected to a reverse osmosis unit. The water temperature is maintained at 25 degrees Celsius to optimize mixing of sugars. This solution forms the neutral base syrup, which will be used in the final product. Blending occurs in a high-capacity horizontal tank fitted with 2 counter-rotating paddles. The sweetener solution is mixed for 5 minutes before receiving the flavored concentrate. Both streams are combined through a Y junction with a static mixer installed in line. As soon as the base and flavor are unified, a light degassing takes place using a vacuum chamber positioned before the storage tank. This step removes trapped air introduced during transfer or agitation. Once degassed, the finished syrup is cooled to 4 degrees Celsius through a tubular heat exchanger before entering carbonation. Carbon dioxide is stored in a bulk tank under pressure and delivered to the carbonation chamber through flow-restricted piping. Syrup enters the carbonator at a controlled rate using a servo-actuated pump. Gas is dissolved by injecting microbubbles into the moving syrup using sintered metal diffusers. Carbonated syrup exits into a buffer tank positioned above the filler. This tank maintains constant head pressure to stabilize flow. The syrup in this tank is kept cold by recirculating chilled water around the vessel jacket. A level sensor manages inflow from the carbonator to prevent overflow. PT bottles are formed on site, starting with preforms loaded into a hopper. Each preform is picked by a rotary arm and placed into a mold. Stretch blow molding begins with heating preforms to 110 degrees Celsius using infrared lamps. Heated preforms are stretched vertically, then expanded with high-pressure air into bottle shape. The finished bottles are transferred by neck holders to the rinsing carousel. A nozzle enters each bottle and injects sterile water to remove particulates. Rinsed bottles move to the filler via a star wheel which positions each neck under a filling valve. The filling machine is isobaric, which keeps bottle pressure equal to syrup pressure. Each filling valve opens when the bottle rises and seals against the valve head. Syrup flows into the bottle until it reaches a fill height, set by vent tubes inside the filler. Filled bottles move to the capping unit by synchronized belts. Caps are fed from a hopper by centrifugal sorter and aligned onto the bottle mouths. A chuck lowers to apply torque and twist the cap until threads lock. Capped bottles exit the machine and pass under a sensor that checks cap presence. From there, bottles enter a labeler which wraps shrink film labels around each one. Steam is applied at the next station to shrink the label tightly to the bottle contour. Each labeled bottle proceeds to the date coding unit, which uses inkjet technology to print production time and batch ID. The code is placed near the bottleneck on a dry area for visibility. Bottles are arranged into rows on a conveyor, where a grouping arm places them into crates. The crates move to a palletizer, which builds vertical stacks using a programmed layer pattern. Full pallets are wrapped with plastic film and moved to storage. Multiple syrup batches are prepared per shift to meet production demand. Each flavor concentrate batch can serve hundreds of liters of syrup. Flavor components are blended using programmable dosing, which adjusts for differences in raw material concentration. Sweeteners are kept warm to maintain viscosity within pumping range. Pipes carrying syrup and concentrate are inclined to assist gravity drainage between batches. At the end of a run, residual syrup is pushed from the line using a slug of water. No manual steps are required between blending and packaging. Each process is actuated by a control system that receives sensor input in real time. Syrup density is confirmed by inline refractometers, which monitor sugar concentration continuously. CO2 solubility is affected by temperature and pressure, so both are monitored at the carbonation point. If syrup warms or pressure drops, gas volume per litre decreases, which affects final mouthfeel. The carbonator compensates by adjusting dwell time or increasing gas injection rate. Bottle fill height is controlled by vacuum venting, which halts flow when liquid touches the vent tube. Changes in bottle wall thickness can cause variation, so backup cameras verify level post-fill. Cap torque is adjusted per cap type and plastic grade to ensure no leaks during storage. Chucks are recalibrated weekly to stay within set force range. Labels are applied with 2 rollers that press opposing edges for full wrap. Label overlap is held with heat-activated adhesive. Preform quality affects bottle strength and clarity. Each batch of preforms is scanned with laser sensors before molding to detect warping or occlusions. Mold temperature is kept constant by circulating oil at 130 degrees Celsius to avoid visual defects. Steam tunnels that shrink labels are fed from an external generator with PID temperature control. Excess steam is extracted by hood fans that channel it to condensers. Label seam alignment is guided by photoelectric sensors that track the mark on the film roll. Filled bottles move at a constant speed, so all label, code, and grouping systems stay in sync. Synchronization is achieved by encoders mounted on main drive shafts which share position data with subsystems. Each syrup blend is traced by batch number from ingredient addition to final packaging. Although this data is recorded, it is not part of the physical process. Blending tanks are equipped with magnetic agitators that mix syrup without shaft penetration. Flavor consistency depends on the timing of concentrate addition and mix speed. The flavor tank uses baffles to prevent vortexing, which could pull air into the blend. Air entrapment can dull flavor strength or reduce CO2 absorption. Grape flavor components include methyl anthranilate and esters, which require uniform dispersion. These are added to the aqueous base in small volume, but have strong impact on profile. Capping speed is linked to fill rate, so as syrup flow increases, the capping turret rotates faster. Caps are pressed with fixed downward force and twisted with servo torque control to prevent over-tightening. Once filled and wrapped, bottles are moved in grouped rows onto collection belts. These belts advance the product toward pallet stations based on sensor feedback. No bottle moves backward once it enters the filling zone. Pepsi manufacturing begins with bulk water intake as the dominant material by mass. Incoming water is routed through coarse mechanical strainers that remove visible solids. The water then moves through layered depth filters that trap suspended particulates by pore restriction. Clarified water enters activated carbon columns where organic molecules bind to the carbon surface. This stage removes odor, causing compounds and trace oxidants. The water is then pushed through reverse osmosis membranes using high-pressure pumps. Ionic species and dissolved minerals are rejected by the membrane structure. The permeate stream exits with tightly controlled conductivity. This purified water is collected in stainless holding tanks with automated level regulation. Temperature conditioning systems adjust the water to a cold range suitable for carbonation efficiency. Sweetener handling begins separately from water preparation. High fructose corn syrup arrives as a viscous liquid stored in heated tanks. Internal recirculation loops prevent phase separation and crystallization. The syrup is metered using positive displacement pumps. Flow meters verify mass accuracy in real time. The syrup line connects to a blending manifold with automated valves. Concentrated flavor base is stored in sealed containers under controlled conditions. The flavor concentrate is dosed in extremely small volumes relative to water. Precision pumps inject the concentrate into the syrup stream. Acid components are added through independent dosing lines. Caffeine is introduced in dissolved form to ensure uniform distribution. Blending occurs inside large agitated mix tanks. Water enters first to establish dilution volume. Syrup follows at a calibrated ratio defined by formulation parameters. Flavor concentrate is injected downstream of the syrup entry point. High-speed impellers generate turbulent flow patterns. This turbulence ensures molecular level mixing of all components. Inline refractometers measure sugar concentration continuously. pH probes monitor acidity throughout the blend cycle. Control systems adjust flow rates dynamically to correct deviation. The completed liquid at this stage is uncarbonated Pepsi base. Carbonation preparation requires cooling before gas injection. The blended liquid passes through plate heat exchangers. Refrigeration circuits lower the temperature close to freezing. Cold liquid improves carbon dioxide solubility. The chilled beverage enters a pressurized carbonation vessel. Carbon dioxide is injected through fine pore diffusers. Gas disperses as microscopic bubbles within the liquid. Tank pressure is elevated to force dissolution. Sensors measure dissolved CO2 concentration continuously. Agitation is minimized to prevent gas loss. The fully carbonated Pepsi is held under pressure until packaging. Container production may occur in line for plastic bottles. PET preforms are loaded into infrared heating ovens. Rotating spindles expose the preforms evenly to heat. The softened preforms transfer into blow molding stations. High pressure air expands the material inside metal molds. The bottle shape forms instantly against the mold walls. Cooling channels solidify the plastic rapidly. Finished bottles exit onto air conveyors. These conveyors suspend bottles by their neck rings. The bottles travel directly to the filling area. Empty bottles enter a rinsing carousel. Jets of filtered air remove dust and debris. Bottles are inverted during this process. They then move into the rotary filling machine. Each bottle engages a filling valve. Carbonated Pepsi flows under controlled pressure. Fill height is determined by internal tube length. Foam generation is minimized through pressure equalization. Filled bottles rotate out of the filler. Excess liquid is returned to the system. Capping occurs immediately after filling. Caps are sorted using centrifugal orientation systems. Properly aligned caps slide down chutes to the capping heads. Each head lowers a cap onto a bottle neck. Torque controlled spindles tighten the closure to specification. Seal integrity depends on precise compression of the liner. Improperly sealed bottles are detected by inspection sensors. Rejected units are removed from the line automatically. After sealing, bottles pass through inversion belts. This allows liquid contact with the cap liner. The contact helps maintain internal cleanliness. Bottles return upright and continue forward. Labeling follows next in sequence. Bottles are synchronized with rotating label drums. Labels are applied using adhesive or heat shrink methods. Registration systems align graphics precisely. Optical scanners verify placement accuracy. Misaligned labels trigger rejection mechanisms. Date coding is applied using non-contact printers. Inkjet nozzles deposit characters onto the bottle surface. Codes include production time and batch reference. Ink is dried instantly using directed air. Bottles proceed toward packaging zones. Grouping conveyors accumulate bottles into fixed counts. Mechanical gates release bottles into pack formation. Shrink film is dispensed over each group. Heat tunnels shrink the film tightly around the bottles. Temperature zones ensure even contraction. Wrapped bundles transfer to palletizing systems. Layers are arranged according to predefined patterns. Robotic arms position bundles with high repeatability. Slip sheets may be inserted between layers. Pallets are built vertically with controlled alignment. Completed pallets enter stretch wrapping machines. Film is stretched and wrapped around the load. Rotational platforms ensure full coverage. Wrapped pallets exit towards storage dispatch. Production follows a parallel, but distinct path. Aluminum coil stock is unrolled continuously. Lubrication reduces friction during forming. Blanking presses punch circular discs from the sheet. These discs are drawn into shallow cups. Redraw and ironing stages elongate the cups. Wall thickness is reduced to precise tolerances. The base is domed for pressure resistance. Trim cutters remove excess material from the rim. Cans undergo washing after forming. Chemical sprays remove oils and residue. Rinsing stages follow to eliminate cleaning agents. Interior coating is applied by spray nozzles. Epoxy liner coats the internal surface. Ovens cure the liner through controlled heating. Exterior printing applies graphics in multiple layers. Each color is applied by separate rollers. Registration control ensures image alignment. A protective overcoat seals the printed surface. Necking machines reduce the top diameter gradually. Multiple stations form the final opening. This reduces lid size and material use. Finished cans are inverted for cleaning. Air and water remove remaining particles. Clean cans enter the filling line. Carbonated Pepsi is dispensed rapidly into each can. Fill volume is controlled by valve timing. Foam suppression techniques maintain accuracy. Immediately after filling lids are applied, aluminum ends are placed on each can. Seamers fold the lid onto the can flange. Double seams are formed through roller pressure. Seam geometry determines seal strength. Inline inspection systems measure seam dimensions. Defective seams are rejected automatically. Filled cans proceed to stabilization conveyors. Gentle vibration equalizes internal pressure. Cans receive date codes next. Inkjet systems mark the base or sidewall. Codes dry instantly without contact. Cans are grouped into multi-pack formats. Collation systems align cans into rows. Paperboard or plastic carriers are applied. Packs move into secondary packaging equipment. Corrugated cases are erected automatically. Packs are inserted into cases. Glue systems seal the case flaps. Cases are stacked onto pallets by robotic systems. Layer patterns optimize stability and space. Pallets are wrapped with stretch film. Barcode labels are applied for tracking. Pallets move to finished goods zones. Throughout Pepsi production, all machines operate under synchronized control. Programmable logic controllers manage timing and coordination. Sensors provide constant feedback on flow and pressure. Recipes define exact ratios and conditions. Automated valves direct fluids precisely. Changeovers adjust machine geometry without manual intervention. Buffer conveyors absorb speed differences. This maintains continuous operation across the line. Cleaning cycles run between production runs. Internal piping is flushed with cleaning solutions. Rinsing restores the system to production readiness. All tanks and lines return to a neutral state. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft-style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks and propagated in sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bacardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bacardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bacardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bacardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, Yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bacardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bacardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bacardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bacardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bacardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bacardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bacardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavored varieties rest longer. Premium products like Bacardi 8 or Bacardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel's share, and oxygen seeps in. Over time, harsh edges soften, flavors deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bacardi's master blenders, trained experts who can detect flavor differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, others deliver weight or spice, others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bacardi's most distinctive processes: charcoal filtration. For Bacardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove color and certain heavy flavor compounds. This process, inspired by Don Facundo Bacardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean, and smooth. Even after aging in oak, the charcoal returns the rum to a near-clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bacardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labeled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bacardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe. To supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bacardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bacardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862, and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bacardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bacardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck, and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats. Open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as white dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x 2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The white dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air-seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame-charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90-plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel-clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100-degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel's share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 2-5% of its volume to evaporation. Maturation time varies by product. Old No. 7 typically ages for 4 to 6 years. Higher end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniel's because blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old No. 7, The spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniel's is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labelling runs to comply with EU, UK, or Asian labelling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavor accuracy. Any deviation from the flavor profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. Auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniel's uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature, fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-co-opted or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols. The core of Coca-Cola's production begins at the local bottling facility. These factories are strategically located around the world to minimize transportation time and maximize freshness. While the Coca-Cola Company maintains control over the flavor concentrate, the bottling partners are responsible for the bulk of production, mixing, bottling, packaging, and distribution. But before anything is mixed, the most vital ingredient must be treated first: water. Water makes up over 85% of Coca-Cola, and its quality directly affects the flavor, clarity, and shelf life of the product. Municipal water is drawn into the plant and subjected to an advanced, multi-stage purification process. It begins with coarse filtration to remove sediment and particulates. From there, the water passes through activated carbon beds, where chlorine and organic compounds are stripped out. Next comes reverse osmosis, or ultrafiltration membranes, which remove dissolved salts, metals, and microorganisms. This purified water then undergoes ultraviolet light treatment, or ozonation, to ensure biological sterility. The goal is to achieve ultra-pure, neutral-tasting water that provides a blank canvas for the Coca-Cola flavor. Constant inline sensors monitor for pH, turbidity, and conductivity, ensuring every liter meets exacting standards before it ever touches the syrup. Next, the flavor base is prepared. The concentrated Coca-Cola syrup arrives at the factory in sealed, food-grade containers. Its precise formulation remains a closely guarded secret, known internally as Merchandise 7X. What we do know is that the concentrate contains sweeteners, acids, caramel coloring, caffeine, natural flavors, and essential oils derived from citrus peels and spices. This concentrate is mixed on-site with additional ingredients, often in a syrup blending station, to create a finished syrup. The syrup blending process is conducted in stainless steel tanks equipped with high-shear mixers and recirculation pumps. These ensure the thick concentrate is uniformly mixed with water, sweeteners, and phosphoric acid, one of the key flavor-defining agents. In most regions, high fructose corn syrup is used as the sweetener, though in others, such as Mexico and parts of Europe, cane sugar is used instead. The blending tanks are temperature controlled and sealed to avoid contamination, and every batch is sampled and lab tested before moving forward. With the syrup mixed and the water purified, the next step is combining the two. This happens in a piece of equipment known as a proportioner. Here, the syrup and treated water are blended at precise ratios, usually around 1 part syrup to 5 parts water, under tight quality control. The proportioner ensures the mix is homogeneous and delivers the same flavor intensity in every can or bottle, no matter where it's made in the world. Now comes the science of carbonation. Carbon dioxide gas, stored in large pressurized tanks on site, is injected into the finished beverage mixture using a carbonator. The carbonator chills the liquid to just above freezing, typically around 33 to 38 degrees F, because cold water can hold more dissolved gas. The beverage passes through a sintered stainless steel sparger, or fine bubble diffuser, which allows the CO2 to saturate the liquid evenly. This gives Coca-Cola its signature effervescence, a process carefully controlled to maintain consistent volumes of CO2, typically between 2.5 and 3.0 volumes. At this stage, the finished product, cold, carbonated Coca-Cola, is transferred to an insulated holding tank under gentle pressure. From here, it is ready to be packaged. And this is where the production line truly comes to life. In a modern bottling plant, packaging lines run at astonishing speeds, filling and capping up to 1,200 bottles per minute or more. But before any beverage enters a container, the containers themselves, whether glass bottles, plastic PET bottles, or aluminum cans, must be cleaned and prepared. PET bottles arrive pre-formed and are blown into full-size bottles on-site using a stretch blow molding machine. This reduces transport volume and increases efficiency. Once formed, each bottle is rinsed or sterilized using ozonated water or clean steam. This eliminates microbial contamination and dust particles. Cans and glass bottles undergo similar sterilization processes, often involving high-pressure air jets or a tunnel washer that uses multiple rinsing stages. Clean containers then move into the filling carousel. This is a high-precision rotary filling machine with dozens of synchronized nozzles, each calibrated to deliver exactly the right volume of Coca-Cola into each bottle or can. The filling occurs under pressure to prevent foaming and loss of carbonation. A vacuum seal may be briefly applied to ensure the gas stays dissolved in the liquid. Immediately after filling, the containers move along the carousel to the capping or sealing station. For PET bottles, tamper-evident screw caps are applied using torque-controlled capping heads. For cans, an aluminum lid is crimped on using a seamer. Glass bottles receive a crown cap applied with pneumatic presses. These closures are crucial not only for sealing in freshness, but also for maintaining carbonation levels throughout the product's shelf life. Once sealed, containers move rapidly to the date coding and inspection stations. Here, inkjet printers mark each unit with its production time, lot number, and best before date. Simultaneously, high-speed cameras and check weighers verify fill levels, cap integrity, label alignment, and overall container quality. Any anomaly triggers a pneumatic arm to remove the item from the line instantly. Bottles and cans are then grouped and packed for shipping. Smaller units may be shrink-wrapped into 6-packs or inserted into cardboard carriers. Larger cases are assembled by robotic arms into corrugated boxes or pallet layers. Palletizers stack the boxes into tall, stable configurations and apply barcoded stretch wrap for secure transport. At this point, Coca-Cola is nearly ready to leave the facility, but not before one last layer of control. Samples from every batch are retained and sent to the quality assurance lab, where a battery of tests is performed. These include sensory evaluations by trained tasters, gas volume testing with CO2 analyzers, Brix level measurement to confirm sweetness, and acid titration for pH control. Only after passing all these checkpoints is the batch released for distribution. The finished product is stored in a climate-controlled warehouse, maintained at ideal conditions to prevent spoilage or bottle expansion. From here, the Coca-Cola is dispatched via refrigerated trucks or temperature-monitored dry vans. Logistics teams coordinate shipments to supermarkets, restaurants, vending distributors, and retail centers using inventory tracking systems that ensure first-in, first-out rotation and traceability in case of recalls. Behind the scenes, the entire system is monitored by a sophisticated SCADA platform that links water purification, blending, carbonation, and packaging into a unified, real-time control interface. Operators can adjust flow rates, tank temperatures, carbonation pressure, and even cap torque from centralized dashboards. Predictive maintenance alerts notify technicians when pumps, motors, or valves deviate from baseline performance, minimizing downtime. The scale is immense. A single Coca-Cola bottling facility can produce several million units per day across various formats, ranging from 8 Oz cans to 2-liter bottles, each undergoing its own production and packaging parameters. Automation is essential, but so is human oversight. Technicians, engineers, microbiologists, and logistics experts all play vital roles in ensuring every sip of Coca-Cola tastes exactly as it should, whether it's opened in Atlanta, Tokyo, or Cape Town. And yet, for all its complexity, the experience of drinking Coca-Cola remain simple: effervescent, sweet, slightly acidic, and unmistakably iconic. Each bottle is a product not just of secret formulas and clever marketing, but of some of the most advanced food manufacturing systems on Earth. From water chemistry to high-speed robotics, from syrup tanks to palletized crates, Coca-Cola's journey from factory to fridge is a meticulously choreographed process, engineered for both speed and perfection. Red Bull starts with its formula, a carefully guarded blend of ingredients that deliver its characteristic taste, texture, and functional effects. At the heart of the recipe is water, which serves as the main ingredient by volume. This water is not simply pumped from a municipal source and used directly. It undergoes multiple purification stages to ensure it is free of any dissolved solids, minerals, or microorganisms that might alter the taste or stability of the drink. The purification typically begins with coarse filtration to remove particulate matter, followed by activated carbon filtration to strip out organic compounds and chlorine, then reverse osmosis to achieve a very low mineral content. The final step often involves ultraviolet light treatment or ozonation to sterilize the water before it enters the production tanks. Once the water is ready, the remaining ingredients are prepared. These include sucrose and glucose for sweetness and energy, citric acid for acidity and flavor balance, taurine as a functional amino acid, caffeine as the stimulant, and B group vitamins like niacinamide pantothenic acid, vitamin B6, and vitamin B12. Each of these arrives at the factory in bulk form: sugars as fine crystals, taurine and caffeine as purified powders, vitamins as either powders or highly concentrated solutions. All are stored under controlled conditions and tested in an in-house quality lab for purity and potency. The creation of the beverage begins with the preparation of a concentrated syrup. In large stainless steel blending vessels, precise amounts of sugar are dissolved in purified water under gentle heat, usually between 50 and 60 degrees Celsius, to speed dissolution without caramelizing the sugar. The glucose syrup, if used in liquid form, is pumped directly into the blending vessel through sanitary pipelines. Once the sugars are fully dissolved, the other functional ingredients, taurine, caffeine, and vitamins, are added in carefully measured doses. This mixing process is critical. Operators rely on automated ingredient dosing systems connected to load cells and flow meters to ensure exact quantities, as even a small deviation could alter flavor or regulatory compliance. Citric acid is then introduced to adjust the pH, giving Red Bull its slightly tart backbone and enhancing stability. Flavors, which are part of a proprietary blend, are also incorporated at this stage. These may include natural and artificial components that together create the drink's distinctive aroma and taste. The mixing tanks are fitted with high-speed agitators to ensure uniform distribution of all ingredients, and the resulting syrup is tested in the lab for Brix, acidity, and flavor profile before moving forward. Once the base syrup is complete, it is diluted with more purified water to bring it to the target concentration for the finished beverage. This final liquid mixture, now containing all flavor and functional components, is chilled to prepare it for carbonation. Carbonation is one of the defining aspects of Red Bull's sensory experience, and it is performed with great precision. The chilled beverage passes through a carbonator where it is brought into contact with carbon dioxide under high pressure. The CO2 dissolves into the liquid with the level carefully controlled. Too little carbonation would make the drink taste flat, while too much could affect mouthfeel or cause excessive foaming during filling. The carbonated beverage is then immediately directed to the filling lines. Red Bull is packaged almost exclusively in aluminum cans, chosen for their lightweight nature, excellent barrier properties against light and oxygen, and recyclability. These cans arrive at the factory in massive stacks of unprinted or pre-printed containers, each one spotless and free from dents or imperfections. Before filling, they undergo a thorough rinse with deionized water or ionized air to remove any dust or debris. The rinsed cans move down the line on high-speed conveyors into the filling carousels. The filling process operates at incredible speed, often hundreds of cans per minute, and is performed in a pressurized environment to maintain carbonation. Each can is filled from the bottom up to minimize turbulence and foaming, then immediately sealed with an aluminum end by a seaming machine. This seam is a precision crimping of the lid to the can body, creating an airtight and watertight seal. Once sealed, each can is inverted briefly to ensure the lid is fully sanitized by contact with the beverage inside, then returned upright. Immediately after sealing, cans pass through automated inspection systems. These use a combination of cameras, sensors, and weight checks to identify any underfilled, overfilled, or defective cans. Any can that fails inspection is automatically rejected and diverted from the main conveyor. Approved cans move on to pasteurization or cold sterilization, depending on the plant's process design. Pasteurization involves heating the cans to a specific temperature for a set time to ensure microbial stability, while cold sterilization uses aseptic filling combined with sterilized containers to achieve the same result without heat. Once the cans are confirmed safe and stable, they head to the secondary packaging area. Here, they are grouped into the familiar 4-packs, 6-packs, or larger cases using cardboard wrap or shrink film. Automated cartoners or shrink wrappers handle this at high speed, often in combination with robotic case packers that load the multi-packs into corrugated shipping cases. The shipping cases are sealed with tape or hot melt glue, coated with batch information for traceability, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability and transported to a climate-controlled warehouse. Although Red Bull is shelf-stable at room temperature, storage away from excessive heat or direct sunlight helps maintain carbonation and flavor over time. From the warehouse, pallets are loaded onto trucks bound for distribution centers and retailers. Given Red Bull's global reach, many of these pallets also enter intermodal shipping containers for transport by rail or sea to other countries. Throughout production, the emphasis on quality and consistency is relentless. Every batch of syrup and finished beverage undergoes analytical testing to confirm caffeine content, vitamin levels, acidity, and carbonation. Sensory panels taste samples to ensure the flavor matches the established profile. On top of that, microbiological testing verifies that no harmful organisms are present, and shelf life trials confirm that the product will remain stable through its intended storage period. The machinery in a Red Bull plant is highly automated, reducing human contact with the product to a minimum. Operators oversee systems via control rooms equipped with touchscreens that display real-time data on mixing temperatures, carbonation levels, filler speeds, and line efficiency. Maintenance crews work behind the scenes to keep pumps, compressors, and conveyors in top condition, as any downtime on a high-speed beverage line can be costly. Sustainability is also a growing focus in Red Bull production. Aluminum cans are already among the most recyclable packaging formats, and many plants source cans with a high percentage of recycled content. Water purification systems are designed to minimize waste, and heat recovery from pasteurization can be used to preheat water for syrup preparation. Efficient compressors and motors reduce energy consumption, and many facilities work to optimize transport logistics to cut fuel use in distribution. What makes the Red Bull process particularly interesting is how tightly controlled and repeatable it must be. The drink's formula is identical worldwide, which means a can produced in Austria should taste exactly the same as one produced in the United States or Asia. Achieving this level of uniformity across multiple plants requires not only identical recipes and ingredients, but also standardized equipment, operating procedures, and quality control protocols. Every plant is essentially a mirror of the others, ensuring that no matter where it's made, Red Bull delivers the same signature flavor, carbonation, and energizing effect. Every can of Monster begins with its ingredients, and the largest component is water. The water used in Monster Energy production is not simply drawn from a tap, it is subjected to a thorough purification process to remove any dissolved solids, organic compounds, or microorganisms that could affect taste, appearance, or stability. The typical sequence starts with coarse filtration to catch sediment, followed by activated carbon filters to strip out chlorine and odors. Reverse osmosis membranes then reduce mineral content to near zero, creating a blank canvas for the flavor formulation. As a final step, ultraviolet light or ozone is used to sterilize the water before it enters the mixing tanks. Next come the sweeteners, functional additives, acids, and flavors that give Monster its distinctive taste and energy-boosting profile. Cane sugar or beet sugar may be used along with glucose or high fructose corn syrup, depending on the variant and market. These sugars arrive in bulk either as crystalline solids or liquid syrup in tanker trucks. Functional ingredients include caffeine for stimulation, taurine as an amino acid additive, and B vitamins like niacin, riboflavin, vitamin B6, and vitamin B12 to support energy metabolism. Some varieties incorporate plant extracts such as ginseng or guarana, which add both flavor and functional appeal. Acids like citric and sometimes malic acid adjust the pH for tanginess and preservation, while natural and artificial flavors create the unique profile for each Monster variety, from the classic green logo flavor to tropical, coffee-based, and sugar-free blends. The first main step in production is the preparation of the concentrate or syrup. In large stainless steel mixing vessels, sugar is dissolved into heated purified water under gentle agitation. If liquid sweeteners are used, they are pumped directly in and blended. Functional powders like caffeine and taurine are carefully weighed and added in controlled sequences to ensure complete dissolution without clumping. B vitamins, which are sensitive to heat, are typically added later in the process to preserve potency. The plant extracts, if used, are measured and incorporated at specific points, often emulsified to ensure they disperse evenly throughout the drink. Flavor concentrates, which can be highly potent, are metered into the mix using precision dosing pumps. These concentrates often contain a mixture of flavor oils, sweeteners, and acids in a stable base that integrates easily into the water-sugar matrix. Because Monster produces a wide variety of flavors, the plant must be capable of switching from one concentrate to another with minimal downtime. A challenge that requires clean-in-place systems to flush and sanitize mixing tanks and pipelines between batches. Once the syrup is fully blended, it is tested in the quality control lab for sweetness, acidity, caffeine content, and flavor profile. The lab team uses sensory analysis alongside instrumental testing to ensure the mixture matches the established standard. Only when it passes these checks is it moved forward. The next stage is dilution and carbonation. The concentrated syrup is blended with additional purified water in large batch tanks to reach the target formulation for the finished drink. This diluted beverage is chilled to near freezing temperatures to maximize the solubility of carbon dioxide during carbonation. The chilled liquid enters a carbonator, where CO2 is injected under high pressure and mixed through fine diffusers or inline mixers. The carbonation level is closely controlled. Too little, and the drink will taste flat. Too much, and it will foam excessively during filling. Once carbonated, the beverage moves immediately to the filling lines. Monster Energy is almost always packaged in aluminum cans, chosen for their lightweight, barrier properties, and recyclability. These cans arrive at the plant in massive pallets of unfilled containers, often printed with Monster's signature claw mark logo and variant-specific graphics. Before filling, each can is inverted and passed through a rinser, which uses either deionized water or ionized air to remove any dust or particles. The cans travel into high-speed rotary filling machines where they are filled from the bottom up to reduce foaming and preserve carbonation. Each filler head dispenses an exact volume, ensuring every can meets legal net content requirements. Immediately after filling, the cans pass into a seaming machine, where an aluminum lid is placed on top and mechanically rolled into place to form a double seam that locks the contents in airtight. This seaming process is a critical control point. Improperly sealed cans can lose carbonation or leak, so seamer performance is constantly monitored. Sealed cans are inverted briefly so that the liquid inside can contact the underside of the lid, which acts as a quick sterilization step. Depending on the plant's process, the cans may then undergo tunnel pasteurization. Moving through a heated water spray tunnel that raises the beverage temperature for a specific time to kill any microorganisms. Or may rely on aseptic filling techniques that eliminate the need for heat treatment. Once pasteurized or otherwise stabilized, the cans are cooled rapidly to prevent heat damage to vitamins and flavors. They then pass through a series of inspection systems. Automated vision cameras check for dents, damaged seams, or incorrect graphics. Check weighers ensure that each can contains the correct amount of product, and any deviation triggers an automatic rejection. Many lines also incorporate inline gas analysis to confirm carbonation levels in the finished product. The approved cans move into the secondary packaging area, where they are grouped into multi-packs. This may involve cardboard carriers, shrink-wrapped bundles, or trays depending on the market. Automated packers arrange the cans in the correct pattern, wrap or enclose them, and send them toward the case packing stage. Here, multi-packs are loaded into corrugated shipping cartons, which are sealed, coated with batch and date information, and stacked by robotic palletizers. Pallets are wrapped in stretch film to secure the load and sent to the warehouse for storage. Even though Monster Energy is shelf-stable at room temperature, it is generally stored in cool, dry conditions to maintain flavor and carbonation quality. From the warehouse, products move through distribution networks to retail shelves worldwide. Behind all of these steps is a rigorous quality control program. The production team pulls samples at every stage: syrup preparation, dilution, carbonation, filling, and post-packaging to confirm compliance with product specifications. Analytical labs test for caffeine content, sugar level, vitamin potency, pH, and carbonation. Microbiological testing ensures that no spoilage organisms are present. Sensory panels evaluate taste, aroma, and mouthfeel to maintain brand consistency. The machinery that makes this possible is heavily automated. Operators work from control panels in climate-controlled rooms, monitoring temperatures, pressures, flow rates, and carbonation levels via touchscreen interfaces. Programmable logic controllers coordinate the entire process, from mixing through palletizing, and sensors throughout the plant send real-time feedback. This automation allows Monster to produce enormous volumes with minimal downtime, while meeting strict safety and quality standards. Sustainability considerations are increasingly built into Monster's operations. Aluminum cans are highly recyclable, and many suppliers provide them with a significant proportion of recycled content. Water purification systems are designed to recover and reuse as much water as possible in non-product applications like cooling or cleaning. Heat from pasteurization is often recovered and used to preheat water for syrup preparation, reducing energy demands. Transportation logistics are optimized to reduce emissions, and some plants have moved towards renewable energy sources for part of their power. What is most striking about Monster Energy production is its consistency. The brand's image may be chaotic and wild, but the drink inside is the product of careful, repeatable processes that leave nothing to chance. Every step is measured, every variable tracked, every can inspected, ensuring that when a consumer pops the tab and hears that sharp hiss of carbonation, they get exactly the flavor, mouthfeel, and energy hit they expect, whether they bought it in a gas station in California or a convenience store in Seoul. The making of a can of Celsius Energy is a study in a modern beverage manufacturing where health-focused marketing meets industrial-scale precision. Although the drink is promoted as a fitness or metabolism-boosting energy beverage, the underlying production process is much like that of other carbonated functional drinks. A carefully balanced formula of water, sweeteners, active ingredients, and flavors blended, carbonated, and packaged under conditions designed to maintain purity, consistency, and shelf stability across millions of units. It begins with the most abundant ingredient, water. Water quality is paramount in Celsius production because any dissolved minerals, organic matter, or off flavors could interfere with the delicate flavor balance and the stability of the added functional ingredients. Purification is achieved through a series of treatments. First, the incoming water is screened through coarse filters to remove particles. Activated carbon filters then strip out chlorine, residual odors, and organic compounds. Reverse osmosis membranes reduce dissolved solids to extremely low levels, creating a neutral base. Finally, ultraviolet light or ozonation is applied to sterilize the water before it enters the formulation tanks. Once the water supply is ready, the functional and flavor ingredients that distinguish Celsius are prepared. Unlike traditional energy drinks that lean heavily on sugar and caffeine alone, Celsius incorporates a blend of caffeine from both synthetic and natural sources, such as green tea extract and guarana seed extract. It also features taurine, B vitamins, vitamin C, and in many varieties, additional plant extracts such as ginger root extract for a warming, metabolism-supporting effect. Some variants are sweetened with cane sugar, while many zero sugar options use non-nutritive sweeteners like sucralose or stevia extract. Acids like citric acid and malic acid are used to balance the flavor profile and help preserve freshness, while natural flavors, often fruit-based, create the distinct taste of each variety, from sparkling orange to peach vibe. The first major step in production is creating the base concentrate or syrup. This happens in large stainless steel mixing vessels equipped with high shear agitators or propeller mixers to ensure complete dispersion of both solids and liquids. For sugar-containing variants, crystalline sugar is metered into the purified water and dissolved at a controlled temperature to speed up the process without causing caramelization. If the formula calls for 0-calorie sweeteners, these are introduced in microgram precise quantities via automated dosing systems, as their sweetness intensity is many times greater than that of sugar. Functional powders such as caffeine, taurine, and vitamin C are weighed with laboratory-grade scales before being added. Plant extracts often arrive as liquid concentrates or fine powders and may require pre-dissolution in a small amount of water or glycerin to ensure they blend smoothly without clumping. For heat-sensitive ingredients like vitamin C, addition occurs towards the end of mixing to minimize degradation. Throughout this stage, the pH is monitored and adjusted as needed, since certain active compounds are more stable within specific acidity ranges. Once all solids are dissolved and liquids are homogenized, flavoring compounds are introduced. These may be natural fruit essences, essential oils, or compounded flavors from specialist suppliers. The flavoring process is highly sensitive. Even slight, over, or underdosing can shift the sensory profile away from the established standard. The completed syrup is sampled and sent to the in-house quality control laboratory for analysis. There, technicians measure sugar concentration, acidity, caffeine content, and other activities and conduct sensory evaluations to confirm taste matches the reference profile. After passing these checks, the syrup is diluted with more purified water to the final formulation strength in large batch tanks. At this stage, the beverage is chilled to near freezing temperatures in preparation for carbonation. Carbonation is one of the signature sensory features of Celsius's sparkling varieties, and it is carried out with precise control over dissolved CO2 content. The chilled liquid flows into a carbonation unit where carbon dioxide gas is injected under pressure, dissolving evenly into the liquid. The goal is to achieve a crisp, sparkling mouthfeel without excessive foam that could cause filling issues. From the carbonator, the beverage is pumped directly to the filling lines. Celsius is typically packaged in slim aluminum cans, often the 12-ounce or 355 milliliter size, chosen for their portability, shelf life stability, and recyclability. The empty cans arrive at the plant in palletized stacks and are fed onto conveyors. Before filling, they undergo a rinse using ionized air or deionized water to remove any dust or particles. The cleaned cans are inverted, then righted, and sent into the filling carousel. The filling process operates at high speed, often hundreds of cans per minute, and is done under conditions that protect carbonation. Each filler head dispenses an exact volume from the bottom up to reduce turbulence. Immediately after filling, the cans move into a seaming machine, where an aluminum lid is placed on each and mechanically crimped to form an airtight seal. This seam is a critical element of the can's integrity, and seaming stations are regularly checked with seam micrometers to verify proper formation. Sealed cans may pass through a pasteurization tunnel, depending on the plant's preferred stability method. In pasteurization, the cans travel along a conveyor under sprays of hot water that raise the internal beverage temperature to a specific target for a defined time, killing any potential microorganisms. Afterward, the cans are cooled quickly to protect heat-sensitive nutrients. In some plants, aseptic filling technology is used instead, allowing the drink to be filled into sterilized cans without the need for post-fill heat treatment, which can better preserve delicate flavors and vitamins. Once cooled, the cans pass through a series of inspection systems. Vision systems scan for dents, label defects, or improper graphics. Check weighers ensure the net content is correct, and any can outside the tolerance is automatically rejected. Inline gas analyzers may measure CO2 content to confirm carbonation consistency. Approved cans enter the secondary packaging stage, where they are grouped into multi-can packs. Cardboard sleeves, shrink film, or tray packs are applied depending on the distribution plan. Multi-packs are collated into corrugated shipping cases, which are sealed with glue or tape and printed with batch codes for traceability. Robotic palletizers stack these cases onto pallets in stable patterns, after which the pallets are wrapped in stretch film to secure them for transport. The finished pallets move into climate-controlled warehouse storage. Celsius products are shelf-stable, but temperature control helps maintain flavor, carbonation, and nutrient stability over the shelf life. From here, pallets are shipped to distributors, retailers, and online fulfillment centers worldwide. Throughout this process, quality control is constant. Samples from each batch are tested for caffeine level, vitamin potency, flavor accuracy, pH, and carbonation before release. Microbiological tests ensure no spoilage organisms are present. Sensory panels evaluate the finished drink for mouthfeel, aftertaste, and aroma, comparing it to the brand standard. Because Celsius positions itself in the better-for-you beverage category, consistency in active ingredient content is especially critical, and certificates of analysis often accompany each production run. Behind the scenes, this is all enabled by a network of highly automated equipment controlled by programmable logic controllers. Operators monitor the process from control stations, adjusting parameters like mixing speed, carbonation pressure, or filler settings as needed. The plant's clean-in-place systems allow tanks, pipelines, and fillers to be washed and sanitized automatically between batches, ensuring hygiene without extended downtime. Sustainability is an increasing focus in Celsius production. Aluminum cans are infinitely recyclable, and many suppliers now provide cans with a high percentage of recycled content. Plants work to reduce water use in cleaning and cooling, recover heat from pasteurization to preheat processed water, and optimize transport routes to cut emissions. Some facilities integrate renewable energy into their operations, such as solar panels or purchase agreements for green electricity. What makes the Celsius production process interesting is the careful balance between functional beverage science and mass-market beverage engineering. While the plant extracts and nutrient additions require precise handling to maintain potency and stability, the large-scale manufacturing environment demands speed and efficiency. The result is a beverage that can deliver consistent taste, carbonation, and nutritional content across millions of cans, while supporting the brand's positioning as a lifestyle-oriented, health-conscious energy drink. Nescafe instant coffee is produced by extracting soluble coffee solids from roasted beans and then drying that extract into stable granules that dissolve fast in water. The process begins with green coffee beans that are cleaned to protect the downstream grinders and roasters. The beans pass over screens that remove stones and oversized debris. Air classifiers lift away light husk fragments and dust. Magnets capture metallic fragments before the beans enter storage bins. Roasting converts the raw beans into a brittle aromatic material that can be milled and extracted. Bins into a roaster at a controlled mass flow. Heat is applied in a programmed curve that drives moisture out first. As temperature rises, the beans expand and internal pressure opens micropores. Sugars and amino acids react and form brown polymers that deepen color. Volatile aroma, compounds form and migrate toward the surface as the bean structure becomes porous. Roast control is managed by time and temperature and airflow. Airflow carries away smoke like volatiles and maintains uniform heat transfer. Roast endpoint is set to balance extraction yield and flavor profile. A lighter roast preserves brighter notes but can reduce solubility. A darker roast increases solubility but can add bitter roast solids. When roasting ends, the beans are cooled quickly to stop further reactions. Cooling air flows through a moving bed, so the beans drop below reaction temperature. Rapid cooling limits over roast drift and protects aroma. The cooled beans move into a degassing period where trapped gases begin to leave. Degassing reduces foaming and pressure issues in extraction. Grinding sets the surface area that controls extraction speed and selectivity. Beans are conveyed to roller mills or hammer mills depending on target particle shape. Roller mills crack and shear the beans into a controlled distribution. Hammer mills impact the beans and can create more fines. The grinder is tuned to create particles that allow fast water penetration, yet avoid excessive fines that clog filters. Particle size is classified after grinding. Screens and air classifiers separate fines from the main fraction. Oversized particles are returned to the grinder. The goal is a narrow band that supports stable extraction bed permeability. A stable bed keeps water flow even and prevents channeling. Extraction is the heart of instant coffee production. Ground coffee is loaded into extraction columns that operate as a countercurrent system. Hot water enters one end of the column train and spent grounds exit the other end. Fresh water meets the most exhausted grounds first. Water becomes progressively richer as it moves toward fresher grounds. Extraction temperature is set to dissolve desired solids while limiting harsh compounds. Higher temperature increases yield and dissolves more bitter fractions. Lower temperature preserves aroma but reduces yield. The system often uses staged temperatures across the column train. Early stages may run hotter for bulk solids. Later stages may run cooler to protect delicate notes. Pressure is used to keep water in liquid form at elevated temperatures. Pressurized extraction improves heat transfer and solubility control. Flow rate is regulated to maintain a target contact time. Contact time controls how far extraction proceeds before the liquid leaves the bed. Too short a contact time wastes soluble solids. Too long a contact time pulls more bitter fractions. The extract leaving the columns contains dissolved coffee solids and suspended, fine particles. Clarification removes those particles to improve final appearance and stability. The extract passes through screens that catch coarse fines. It then enters a centrifuge that separates suspended solids by density. Clarified extract flows forward, while sludge is removed for separate handling. Fine filtration can follow centrifugation. Depth filters capture remaining microfines that would create haze. Filter choice balances clarity and flavor. Too aggressive filtration can strip flavorful colloids. Too little filtration can leave sediment in the final granules. At this point, aroma management becomes important because extraction and clarification drive off volatile compounds. Many lines capture aromatics from roasting and grinding and early extraction vents. These aromatics are condensed into an aroma concentrate. The concentrate is stored cold to slow loss. It is added back later after drying or near the end of concentration. The clarified extract is still mostly water, so it must be concentrated. Evaporation removes water and raises solids content. Concentration is usually done under vacuum, so boiling occurs at lower temperatures. Lower boiling temperatures reduce thermal damage and preserve flavor. Falling film evaporators are common because they expose liquid as a thin film. Thin films evaporate fast and limit residence time. Solids concentration is controlled to a target viscosity suitable for drying. Too low a solids level wastes energy in drying. Too high a solids level becomes too viscous to atomize in a spray dryer. Sensors track density and refractive index as proxies for solids. Flow control keeps the evaporator steady so the concentrate remains consistent. Some product streams include a mild heat treatment during concentration. This can stabilize the concentrate by inactivating enzymes and reducing microbial load. The heating profile is kept brief to avoid cooked notes. Vacuum evaporation already reduces thermal stress, so the heat treatment can be minimal. After evaporation, the concentrate is cooled to a controlled temperature. Cooling protects aroma and sets viscosity for the selected drying method. The process then splits depending on whether the line makes spray-dried coffee or freeze-dried coffee. Spray drying converts concentrate into powder by atomizing it into hot air. The concentrate is pumped to an atomizer that forms fine droplets. A rotary wheel atomizer can create a narrow droplet size band. A pressure nozzle atomizer can create different droplet distributions. Droplet size controls final particle size and bulk density. Droplets enter a drying chamber with heated air. Water evaporates from the droplet surface first. A skin forms, and then moisture diffuses outward through the skin. The droplet shrinks and solidifies into a particle. Air temperature is controlled, so drying is rapid but not scorching. Outlet air temperature is a key indicator because it reflects remaining moisture. Powder leaving. The drying chamber is separated from air in cyclones. Cyclones spin the airstream and throw particles outward. Fine particles are captured efficiently and then discharged. Additional bag filters capture the finest dust. The recovered powder is cooled to prevent caking. Final moisture is set low enough for stability, but not so low that particles become overly fragile. Spray-dried powder can be too dusty and too fast dissolving. Many lines agglomerate it to create larger porous granules. Agglomeration starts by re-wetting powder lightly with steam or water mist. Particles become tacky on the surface. They collide and stick into clusters. Warm air then dries the clusters and locks in the structure. The resulting granules have larger size and better sink behavior in water. Freeze drying follows a different path that preserves aroma and creates crisp granules. Concentrate is first chilled and then frozen into a solid slab or into pellets. Freezing speed controls ice crystal size. Larger ice crystals create larger pores after sublimation. Smaller ice crystals create finer pores and can slow dissolution. Frozen coffee enters a vacuum freeze dryer. Under vacuum, the ice sublimates, which means it goes from solid to vapor without melting. Heat is added gently through shelves or radiant plates. Sublimation leaves behind a porous matrix of coffee solids. The structure is brittle and breaks into irregular granules. After freeze drying, the dried slab is milled or fractured into target granule size. Screening separates fines and oversize. Oversize is reduced further. Fines can be recycled into agglomeration or blended depending on product targets. The granules are then conditioned to equalize moisture and temperature. Aroma restoration is typically applied after drying because high heat and vacuum remove volatiles. Aroma concentrate is dosed onto the dry granules in a closed blender. The granules tumble while a fine spray coats their surfaces. The coating is absorbed into pores and binds by capillary action. The system controls spray rate to avoid wet spots that cause clumping. Some lines also perform a light surface polishing. This step reduces dust and improves flow in packaging. Polishing can be done by gentle tumbling that knocks off loose fines. It can also include a tiny amount of food-grade anti-caking agent. The application is kept minimal, so it does not change flavor release. Quality control at this stage focuses on moisture and bulk density and dissolution time. Moisture affects shelf stability and clumping. Bulk density affects dosing in jars and sticks. Dissolution time affects consumer experience in hot and cold water. Particle size distribution is measured because it controls flow and dust. Blending is used to keep flavor consistent across production lots. Granules from different runs can be blended to average variations. Blending equipment uses gentle paddles to avoid crushing. The blender also equalizes aroma addition across the batch. Sampling confirms uniformity by checking aroma intensity and color and soluble solids. Nesquik chocolate drink mix is manufactured by turning cocoa and sweetener into a free-flowing instant powder that wets fast and disperses without floating clumps. Production starts with bulk ingredient receiving and conditioning. Sugar arrives as granulated crystals and moves into silos with controlled humidity. Cocoa powder arrives in lined totes and is kept in a dry room to prevent caking. Milk-derived powders can be included for creaminess, and they are stored cold enough to stay free-flowing. Minor ingredients like salt and flavors arrive in sealed drums to protect aroma strength. Vitamin and mineral premixes arrive as low-dose powders that require tight segregation for accurate dosing. The line begins with particle preparation because every downstream step depends on predictable flow. Sugar is screened to remove oversized crystals that can separate during blending. Sugar fines are managed because excessive fines increase dust and can make the mix pack too tightly. Cocoa is sifted through vibratory screens to break soft agglomerates. Any fibrous lumps are removed to prevent specks in the final product. Milk powders are sieved with larger mesh to protect fragile particles from unnecessary grinding. Cocoa powder requires special handling because it is hydrophobic and tends to float. The powder surface contains natural fats that repel water. This property is the main reason Nesquik needs instantizing steps. The process, therefore, focuses on building granules that pull water in quickly. It also focuses on adding emulsifiers that lower surface tension and improve wetting. Weighing and batching starts once each ingredient is within specification. Large-scale ingredients are metered by loss in weight feeders. The feeders deliver sugar and cocoa at controlled rates into a pre-blend hopper. Medium-scale ingredients like milk powder and maltodextrin are metered through secondary feeders. Very low-dose ingredients like vitamins are added through micro feeders with screw dosing. Each feeder is calibrated so the recipe ratio stays stable across long runs. Pre-blending is used to prevent micro-ingredient streaks. Sugar becomes the carrier phase because it has high mass and flows well. Micro-ingredients are first blended with a small portion of sugar in a ribbon blender. This creates a dilute premix with uniform distribution. The premix then rejoins the main sugar stream and reduces the chance of hot spots. The main blending step combines sugar and cocoa into a uniform base. A high-capacity ribbon blender or plowshare mixer is common here. The mixer creates strong folding action that lifts powder and then lets it fall through a shear zone. Cocoa is dispersed into sugar so the color becomes even. Mixing time is controlled because overmixing can create electrostatic charging and dust. Undermixing leaves cocoa streaks that show up as dark clusters in scoops. Flavor addition happens during the main blend or just after it. Vanilla flavor is often added as a liquid or as a dry encapsulated powder. Liquid flavor is sprayed through a fine nozzle into the moving powder bed. The spray rate is low to avoid creating wet clumps. The mixer speed is increased briefly to distribute the liquid film. Dry flavor powders are easier to distribute, but they still need good agitation to avoid pockets. Salt is added in small quantity, and it must be dispersed evenly. Salt crystals can segregate if their size differs from sugar. Many lines use fine salt or salt dissolved into a small liquid addition. When salt is added as a dry powder, it is often included in the premix step. This reduces segregation later in transport. If the formula includes vitamins, the process emphasizes gentle but thorough distribution. Vitamin premixes can be sensitive to heat and moisture. They are added after any warm steps to reduce loss. They are also protected from intense shear that could break protective coatings. The blender uses a defined sequence so the vitamins are introduced after the bulk powders have already become uniform. At this stage, the powder is blended, but it still has poor instant properties. Cocoa will still float and form islands on water. The next stage is instantizing, which converts fine powders into porous granules that sink and disperse. There are several ways to instantize. A common route is agglomeration with a wetting step followed by drying and cooling. Agglomeration starts by feeding the blended powder into a controlled chamber. The powder forms a moving curtain or a fluidized bed. A binder is then applied as a fine mist. The binder can be water or sugar syrup depending on the target density. The binder lightly wets particle surfaces and makes them tacky. Tacky particles collide and stick into clusters. These clusters grow into granules as more powder adheres. Granule growth must be controlled tightly. If binder is too high, the granules become large and hard. If binder is too low, the granules remain dusty and fragile. Airflow and chamber turbulence control collision rate. Residence time controls final size. The process aims for granules that feel light and porous. Porosity is important because it creates capillary channels that pull in liquid. A key improvement step is lecithination. Lecithin is an emulsifier that improves wetting and reduces surface tension. Lecithin can be applied as a liquid spray onto moving powder. It can also be applied as a solution in a volatile carrier. The spray coats granule surfaces and migrates into pores. This makes cocoa less hydrophobic in the cup. The dosage is low, but the impact on dispersibility is large. When lecithin is applied, the process must avoid creating shiny wet spots. Spray droplets must be small and evenly distributed. The bed must be moving vigorously so the film spreads. Temperature is controlled, so lecithin stays fluid during application. After application, the granules are dried slightly to lock the surface condition. Drying follows agglomeration because binder adds moisture. Drying is done with warm air moving through the granule bed. Air temperature is chosen to remove water without changing flavor. Too much heat can drive cocoa volatiles off and dull aroma. Too little heat leaves moisture that causes caking in the jar. The dryer controls inlet temperature and outlet humidity to reach a target moisture. Drying also stabilizes structure. As moisture leaves, the binder creates bridges between particles. These bridges set granule strength. Strong enough bridges prevent breakdown into dust. Weak bridges create fines during conveying and filling. The process tunes drying time to meet a target crush strength. That crush strength must still allow fast dissolution in the cup. After drying, the product is cooled. Cooling prevents condensation in packaging and reduces clumping risk. Cooling air is dehumidified, so it does not add moisture. The granules exit at a temperature close to the packaging room temperature. This prevents moisture migration when the product enters sealed packs. Screening and sizing occur after cooling. Vibratory screens remove oversized agglomerates that would dissolve slowly. Screens also remove fines that create dust and poor wetting. Oversize can be milled lightly and returned to agglomeration feed. Fines can be recycled as seed material for new agglomeration. Recycling is controlled, so the powder does not build up too much fine content. Some lines add a final dry blend step after agglomeration. This can be used to add heat-sensitive vitamins. It can also be used to add a small amount of anti-caking agent. Anti-caking agents are used at very low levels to keep flow stable. They are distributed with gentle mixing to avoid breaking granules. The blend time is short to protect structure. Density control is a major target for drink mixes. Bulk density affects spooning and packaging, volume and consumer dosing. Agglomeration tends to lower density because it creates porous granules. The process tunes binder and airflow to hit a defined density band. Too low, a density makes scoops inconsistent. Too high a density can reduce instant performance. Flowability control is equally important. Granules must flow through hoppers without bridging. They must also settle consistently in jars. Flow is improved by uniform granule size and low moisture and smooth surfaces. Excess fines degrade flow because they increase cohesion. The screening stage, therefore, has a strong influence on packaging efficiency. Color uniformity is checked because cocoa distribution must remain stable. Color drift can indicate segregation or inadequate mixing. If the product includes added micronutrients, the line checks distribution by sampling and chemical analysis. Uniform distribution is achieved mainly by the premix approach and by stable blender loading. The product then moves to packaging feed systems. Gentle conveyors are used to protect granules from breakage. Bucket elevators can be used with low drop heights. Pneumatic conveying is possible, but it can create fines if velocities are high. When pneumatic systems are used, the line uses low-velocity dense phase conveying. Bends are designed with large radii to reduce impact. Packaging for Nesquik can be in jars or canisters or sachets. For canisters, the product is filled by volumetric auger fillers. The auger rotates and dispenses a controlled volume of granules. The fill weight depends on bulk density, so density must remain stable. Check weighers confirm the filled mass and reject outliers. The canister is then capped with controlled torque to maintain a moisture barrier. Starbucks coffee starts as green beans that are transformed by controlled roasting, rapid cooling, precision grinding, and oxygen-managed packaging, so flavor remains stable until brewing. Green beans arrive as a hard, dense seed with moisture locked. Inside cell structure, The first job is cleaning, because even small hard contaminants can damage rollers and grinders. The beans pass through screens that remove stones and broken fragments. Air separation lifts away chaff and dust. Magnets capture metallic particles before the beans enter storage bins. Storage is designed to keep bean moisture and temperature steady. Beans are blended from different lots to hit a target profile before roasting begins. This blending step is a physical averaging process. It reduces variability in density and moisture that would otherwise shift roast development. Roasting begins with accurate feed control. Beans enter a roaster at a fixed mass rate, so heat transfer remains consistent. Hot air and heated metal surfaces raise bean temperature in a staged curve. Early roasting drives off free moisture. Steam leaves the bean and pressure builds inside pores. The bean structure expands and becomes more porous as internal water turns to vapor. As temperature rises further, chemical reactions generate color and aroma precursors. Sugars and amino acids react and produce brown polymers that deepen color. Oils migrate toward the surface as the bean matrix opens. Gases form inside the bean and create internal pressure that changes cracking behavior. The roast curve is adjusted so reactions progress without scorching the exterior. Airflow is a main control lever during roasting. Higher airflow increases convective heat transfer and carries away smoke like volatiles. Lower airflow increases contact time of vapors and can intensify roast notes. Exhaust control keeps the roast environment stable, so each batch follows the same thermal history. The roast endpoint is defined by bean temperature and time at development conditions. A shorter development phase preserves brighter notes but can reduce solubility. A longer development phase increases solubility and roast character. The endpoint also influences how easily the bean grinds. A darker roast fractures more easily and produces more fines at the same grinder setting. When the endpoint is reached, the beans must be cooled fast. Cooling stops reactions that would continue from residual heat. Beans drop into a cooling tray or a cooling conveyor. High airflow pulls heat out rapidly and reduces carryover roasting. The target is a uniform final bean temperature, so later packaging does not trap heat and create condensation. After cooling the beans, enter a degassing phase. Roasted beans contain carbon dioxide trapped in pores. Degassing releases gas gradually and changes how the coffee behaves in packaging. If beans are packed too soon, pressure can build inside bags. If beans degar too long, the most volatile aromas can decline. The process chooses a defined rest window that balances gas release and aroma retention. Quality sorting can occur after cooling. Optical sorting can remove scorched beans and pale beans. Density sorting can remove light defects that roast differently. This step tightens consistency in the final bag, because even a small number of off beans can alter brewed cup perception. From this point, production splits into whole bean and ground coffee paths. Whole bean coffee moves toward packaging with minimal mechanical stress. Ground coffee requires additional size control because particle distribution defines extraction speed in the brew. Grinding begins with grinder selection based on product format. Roller mills produce a more uniform distribution with fewer extreme fines. Burr-style industrial grinders create a controlled cut with predictable heat generation. Grinder settings define the median particle size and the tail of fines. The fines fraction matters because it drives bitterness and slows flow in filter brewing. Temperature control during grinding protects aroma and reduces clumping. Grinding generates heat from friction and impact. If coffee warms, too much volatile compounds flash off. Warm grounds also pack and bridge more easily in hoppers. The line manages temperature by controlling throughput and by using cooled air or staged grinding. After grinding, the coffee is classified. Vibratory screens or air classifiers remove oversized fragments and reduce the fraction of dust. Oversized fragments can be returned to the grinder. Excess dust can be blended into other streams in controlled amounts or removed depending on target. Classification improves brew repeatability and improves fill accuracy in packaging. Aroma management becomes more critical once coffee is ground. Grinding exposes fresh surface area and accelerates oxidation. The process, therefore, reduces oxygen exposure time between grinding and sealing. Conveying is often enclosed and may use inert gas in certain steps to reduce oxygen pickup. The goal is to keep oxygen away from oils on particle surfaces. Packaging is built around barrier films and controlled headspace. Bags or canisters are formed and then filled by weight. Auger, fillers, and vibratory feeders deliver grounds in measured pulses. Fill chutes are designed to reduce dust and keep seal areas clean. Weight checks confirm each unit meets target. For whole bean bags, the filler drops beans gently to avoid fracturing. Fractured beans create fines at the bottom of the bag. They also create more surface area for oxidation. Drop heights are minimized and chutes use smooth curves rather than sharp bends. Many coffee bags use a one-way degassing valve. The valve allows carbon dioxide to escape without letting oxygen in. This supports earlier packaging because gas can leave after sealing. It also reduces bag swelling during distribution. Valve application is done as part of bag manufacturing or as an inline step before filling. Sealing closes the package and locks in the controlled atmosphere. Heat seals must be strong and continuous. Seal jaws apply temperature and pressure for a defined dwell time. If dust sits in the seal zone, the seal can leak. The line, therefore, controls dust by extraction and by nozzle cutoff design. Once sealed, the packages move through coding and inspection. Vision systems can confirm seals and valve presence. Check weighers confirm net weight. Metal detection can be used as a final protection step. Units are then packed into cases with orientation that protects valves and reduces crushing. Peanut butter production begins with the bulk intake of raw, shelled peanuts delivered in containers or silos. Peanuts are gravity-fed into hopper systems equipped with vibratory feeders that control the rate of flow into the cleaning section. Cleaning involves sequential mechanical separation units, including air classifiers, rotary drum screens, and gravity tables. Air classifiers remove lightweight debris using high-velocity airstreams. Rotary screens separate based on particle size, discarding small fragments, sticks, and foreign seeds. Gravity tables use differential vibration and airflow to isolate denser whole peanuts from lighter defective material. Cleaned peanuts are transferred via bucket elevators into temporary storage bins prior to roasting. Roasting is carried out in continuous belt roasters or rotary drum roasters depending on line capacity. Peanuts are conveyed in a single layer through a thermal tunnel with forced hot air. Drum roasters use direct heat combined with rotating tumbling action. Roasting temperature ranges from 160 degrees Cs to 180 degrees Cs, with residence times of 25 and 40 minutes. Moisture sensors at the exit point ensure target moisture reduction to below 2%. Roasting also develops flavor and reduces microbial load. Cooled air is forced across the roasted peanuts immediately upon exit. Cooling conveyors equipped with perforated belts and axial fans reduce peanut temperature to below 35 degrees Celsius to prevent oil migration or condensation. Peanuts are held in cooled hoppers with agitation to prevent bridging before entering the blanching process. Blanching removes the outer skin and splits the peanuts. This is performed in two ways: dry blanching or water blanching. Dry blanching involves friction rollers that rub off the skins as peanuts pass through serrated cylinders. Water blanching involves immersion in hot water, followed by belt conveyors fitted with rubber rollers. In both methods, skin fragments are removed by aspiration or vacuum collection systems. Split peanuts pass through inspection belts or optical sorters to remove discolored, moldy, or damaged halves. High-speed cameras scan each peanut and trigger air jets to divert off-spec material. Sorted peanuts are collected in surge hoppers and metered into grinders. Peanut grinding is performed in 2 stages: primary size reduction and emulsification. The first stage uses a hammer mill or disc attrition mill. Peanuts are fed into a chamber with rotating blades or abrasive plates. The initial grind reduces particle size to around 300-500 microns. The paste is then pumped into a second stage colloid mill. The colloid mill performs high shear homogenization between a rotor and stator, reducing particle size to below 100 microns. Rotor speeds exceed 3000 RPM, and the grinding gap is adjustable for texture control. The grinding process also generates frictional heat, raising product temperature to 60-80 degrees Celsius, which reduces viscosity and facilitates emulsification. During the second stage grinding, or immediately afterward, stabilizing agents and additives are introduced. Common stabilizers include fully hydrogenated vegetable oils, such as rapeseed or cottonseed oil. These are pre-melted in jacketed tanks and dosed using heated transfer pumps. Stabilizer addition typically ranges from 1 to 2% by weight and is controlled with flow meters. For sweetened or flavored varieties, additional ingredients such as sugar, salt, molasses, or cocoa powder are added through powder feeders or liquid dosing pumps. These materials are pre-weighed and incorporated in line using dynamic mixers with static mixing elements or turbine blades to ensure rapid dispersion into the viscous peanut paste. After additive incorporation, the peanut butter undergoes a degassing phase. The hot paste is transferred to a vacuum chamber or degassing tank where air bubbles are removed. The system applies vacuum pressure between 0.7 and 0.9 bar while slowly agitating the product to avoid entrapping more air. This step improves texture and packaging stability. Degassed product flows into surge tanks equipped with slow-speed agitators and thermal jackets to maintain fluidity. Temperature is held between 55 to 65 degrees Celsius to facilitate downstream handling. Product is then directed toward the packaging line via sanitary lobe pumps, which provide high volume transfer without shear. Before filling, the peanut butter may be passed through a scraped surface heat exchanger to adjust temperature precisely. The system uses rotating scraper blades inside a jacketed tube to maintain heat transfer efficiency without fouling. Outlet temperature is held constant, typically 50-55 degrees Celsius, for optimal flow into containers. Packaging is performed on high-speed, servo-driven filling lines. Empty jars made of PAT or PP plastic are depalletized and placed onto the conveyor. Each jar passes through an ionized air rinser that removes particulate matter. Clean jars are indexed into a rotary filler with multi-nozzle heads. Volumetric piston fillers or mass flow filling systems dispense precise quantities of peanut butter into each jar. Fill levels are controlled within plus 0.5% tolerance. Nozzles are heated or jacketed to prevent clogging due to cooling product. Some systems use bottom-up filling to prevent air entrapment and surface voids. After filling, jars proceed to the capping station. Caps are sorted and aligned using centrifugal feeders or vibratory bowls, then applied and torqued by rotary chuck cappers. Torque sensors monitor seal integrity, and improperly sealed jars are rejected automatically. If induction sealing is required, a foil liner is placed inside the cap. After capping, jars pass under an induction sealer where a high-frequency electromagnetic field heats the foil, bonding it to the jar rim. The seal creates a hermetic barrier that prevents oxygen ingress and oil separation. Labeled jars move to a wraparound or pressure-sensitive labeling station. Labels are applied using servo-controlled applicators, and optical sensors verify alignment and barcode presence. Rejected units are diverted to inspection lanes. Coded printing systems, typically thermal inkjet or laser, apply batch numbers and date codes to the lid or shoulder of each jar. The print system is synchronized with the conveyor speed to ensure clear, consistent marking. Jars are grouped into sets using collation conveyors and loaded into corrugated cartons or shrink-wrap trays. Case packers use robotic arms or mechanical pushers. Sealed cases are labeled with logistic codes and moved to palletizers. Palletizing systems stack cases using programmed layer patterns. Slip sheets are added as needed, and completed pallets are stretch-wrapped with plastic film to stabilize the load for transport. Each pallet receives an RFID tag or barcode label for warehouse tracking. Throughout production, inline sensors monitor critical parameters. These include product temperature, flow rate, fill weight, torque, seal integrity, and label placement. Data is logged by the Central Manufacturing Execution System and linked to batch tracking systems for traceability. Process water used in cleaning and ingredient dissolution is stored separately and heated as needed. All process equipment is connected to CIP systems that circulate detergent and rinse solutions through pipes, tanks, pumps, and valves at scheduled intervals. Cleaning sequences are validated using conductivity, temperature, and flow sensors. Environmental conditions such as air, temperature, humidity, and particulate levels are regulated in processing areas using HVAC systems with HEPA filtration. Maintaining a controlled environment prevents moisture pickup by roasted peanuts and ensures consistent flow behavior of the peanut paste during grinding and filling. Roasting profiles are monitored using thermal sensors and data loggers. Temperature curves are logged and compared against reference curves to ensure even development across peanut batches. Real-time moisture analyzers positioned at the roaster exit verify dehydration targets. Particle size of the final peanut butter is measured using laser diffraction or sieving techniques. Target particle size is typically below 30 microns for smooth varieties and above 100 microns for crunchy variants. Crunchy peanut butter includes the addition of roasted peanut granules, which are prepared separately using coarse grinders and added post-homogenization under low shear to maintain particle integrity. Oil. Separation resistance is measured during quality control using centrifuge testing or accelerated shelf life studies. Stabilizer effectiveness is confirmed through oil migration testing at elevated temperatures over time. Nutella production begins with the individual preparation of its components: hazelnuts, sugar, cocoa powder, vegetable oil, skimmed milk powder, lecithin, and vanillin. Each raw material is handled separately in dedicated systems to ensure proper particle size, mixing compatibility, and thermal behavior before integration. Hazelnuts are received shelled and pre-cleaned. They are conveyed through pneumatic lines into vibratory feeders that regulate flow into pre-roasting storage silos. From these silos, hazelnuts are metered into a continuous roasting system. Roasting occurs in horizontal convection tunnels or rotating cylindrical chambers, typically at 140 degrees 160 degrees C for 20-25 minutes, depending on kernel moisture. The goal is to reach a final moisture level below 2% and to initiate flavor development. Post-roasting, nuts are directed into cooling drums or belt coolers. Forced ambient air lowers kernel temperature to below 30 degrees Celsius before further handling. The next step is blanching, where the brown skin is removed. This is done using mechanical friction rollers or pressurized steam exposure, depending on the desired throughput. Skin is separated by aspiration. The blanched nuts are then split and sorted by size via oscillating sieves, and undersized fragments are diverted. Cleaned, roasted hazelnuts are passed through a primary grinding phase using disc mills or pin mills to produce a coarse meal. This intermediate product is directed into a secondary grinding stage, often a ball mill or high-speed impact mill, which reduces particle size to a fine paste. Typical particle sizes are reduced to under 30 microns at this stage, producing a flowable hazelnut slurry with partial oil release. In parallel, sugar is handled separately. Granulated sugar is milled using air-classifying impact mills to reduce particle size and ensure dissolution in the final product. The resulting fine sugar powder is transferred pneumatically to dosing silos. A similar dry handling system is used for skimmed milk powder, which is fed into mixers via enclosed screw conveyors. Cocoa powder is stored in low humidity silos and transferred through sealed auger systems to prevent moisture absorption. It is typically defatted and pre-sifted to avoid clumps or oversized particles. All powdered ingredients, sugar, milk, and cocoa, are dry blended using horizontal ribbon blenders. These blenders operate at low speed to achieve uniform mixing without generating excess dust. The vegetable oil, primarily refined palm oil, is kept in liquid state in temperature-controlled storage tanks maintained at 45 to 50 degrees C. Oil is pumped through inline filters and metered into mixing systems via flow control valves. The oil acts as the continuous phase for the final emulsion and must be dosed with high consistency. All components are transferred into a batch mixing system, a stainless steel planetary mixer, or a high viscosity processing vessel equipped with anchor agitators. The sequence starts with oil and hazelnut paste, followed by gradual incorporation of the powdered mix. Agitation is applied in stages, with high torque, low speed mixing used for initial wetting and medium speed agitation for full dispersion. Lecithin, added to control emulsion stability and flow, is stored in small heated tanks and introduced last. It is pre-mixed with a portion of the oil phase and dosed via peristaltic or gear pumps. Concentration is typically around 0.3% of the total mass. Vanillin, in synthetic form or as part of a flavoring premix, is injected at low concentrations and blended briefly under vacuum to prevent volatilization. The batch undergoes a refining stage using a 5-roll or 3-roll mill. The paste is pressed through steel rollers, reducing particle agglomerates and improving surface smoothness. The rollers operate at progressively higher speeds to create shear differentials, compressing solids and distributing fat evenly. Target final particle size is below 25 microns. After refining, the product is transferred to a conche, a jacketed horizontal mixer equipped with large mixing blades. The conching phase continues kneading at elevated temperatures of 50-60 degrees Celsius for 1 to 3 hours. This step enhances mouthfeel, disperses volatile compounds, and improves gloss by coating all particles with fat. Upon completion, the paste moves to a vacuum degassing tank where trapped air is removed. Vacuum is applied at 0.8 to 0.9 bar, while slow paddles maintain circulation. This step prevents air pockets in packaging and reduces oxidative degradation. The degassed product is homogenized through a low shear inline mixer to stabilize viscosity. The finished spread is transferred via jacketed pipelines to holding tanks prior to filling. These tanks are fitted with variable speed agitators and are temperature controlled at 40-45 degrees Celsius. A load cell system measures tank contents, coordinating flow to the packaging line. Transfer is performed with sanitary-grade rotary load pumps for accurate low-shear movement of viscous material. In the filling area, jars are supplied via unscramblers and aligned onto conveyors. They pass under vision cameras to confirm shape and cleanliness. Filling is done using servo-controlled piston fillers or mass flow metering systems. Fill nozzles are jacketed and temperature controlled to maintain flow characteristics. Fill volumes are typically accurate to within plus 0.5%. After filling, jars are sealed with aluminum foil using induction sealing. A liner is embedded inside each cap. When the cap is torqued onto the jar and passed under the induction head, an electromagnetic field heats the foil, bonding it to the jar rim. This creates an oxygen barrier and prevents oil migration. Caps are applied using rotary or inline capping machines with torque monitoring. If torque deviates from preset values, jars are rejected. Sealed jars move to the labeling station, where pressure-sensitive or shrink-wrap labels are applied. Labeling heads are adjusted for jar geometry and verified by optical sensors. Next, jars are passed under thermal inkjet printers, which apply date codes and batch identifiers. Printers are aligned with conveyor timing to ensure sharp, legible printing. Codes are verified by barcode readers or OCR systems. Rejected jars are diverted using pneumatic pushers. Labeled jars are grouped into sets using automated collation conveyors. Depending on destination, they may be packed into cardboard cartons or shrink-wrapped into trays. Cartoning machines erect boxes, load jars, and apply closure glue automatically. Case packers then arrange cartons into shipping cases with robotic arms. Shipping cases are sealed using hot melt glue applicators or tape dispensers and labeled with printed logistics data. The labeled cases are scanned, weighed, and conveyed to a palletizing station. Robotic palletizers stack cases according to optimized patterns, using vacuum or mechanical end effectors. Pallets are wrapped using rotary arm stretch wrappers. Film is tensioned to maintain structural integrity without distorting the cartons. Pallets are tagged with scannable barcodes or RFID labels for traceability. Throughout the entire production process, all operations are controlled and logged by a PLC-driven SCADA system. This includes ingredient dosing, thermal profiles, particle size measurements, fill volumes, torque levels, and packaging throughput. Parameters are displayed on HMI terminals and stored in batch records for traceability. Strawberry jam manufacturing begins with bulk delivery of strawberries in refrigerated containers. The fruit arrives pre-sorted or in raw form depending on source. Upon unloading, strawberries are tipped into stainless steel flume tanks where they are submerged in chilled water to reduce field heat and initiate washing. The strawberries are conveyed out of the wash tank using cleated food-grade belt elevators. A high-pressure spray bar located at the discharge point removes surface contaminants. Excess water is removed by air knives or centrifugal dewatering systems. Cleaned fruit is conveyed to the inspection station. At the inspection stage, strawberries pass over a slow-moving belt or roller table equipped with manual or optical sorters. Defective, underripe, or foreign objects are removed. High-resolution cameras with multispectral imaging may be used for automatic defect detection. Rejected items are separated using pneumatic actuators or diverters. Clean, sorted strawberries are directed to the hulling station. Hulling machines use rotating rubber fingers or mechanical plungers to remove the calyx and stem. The removed portions are separated by air aspiration. Hulled fruit is transferred to a temporary buffer hopper before size reduction. The hulling hopper meters strawberries into a dicing or pulping system. Dicing machines use oscillating blades to produce uniform fruit pieces. For homogeneous jam, fruit is passed through a finisher or pulper equipped with perforated screens and rotating paddles to produce a consistent puree. Screen aperture determines the level of texture in the final product. Pulpy fruit mass is weighed using inline load cells or flow meters and directed to a batching tank. In parallel, sugar is conveyed from silos or bulk bags into a dry blending unit. Sugar is sometimes preheated or dissolved in deionized water to create a syrup. This is controlled by mass flow regulation and prepared in jacketed mixing tanks equipped with agitators. Pectin is added either as a powder or as a pre-dispersed liquid. Powdered pectin is mixed with a portion of sugar to prevent clumping during hydration. The blend is fed into the batching tank via screw feeders or high shear dispersers. The type and concentration of pectin depend on the desired gel strength and fruit acidity. Citric acid is introduced to adjust pH, typically to the range of 3.1-3.4, which optimizes pectin gelation. Acid is dosed from a separate tank using peristaltic pumps, monitored by inline pH probes. The exact amount is calculated based on the natural acidity of the strawberry pulp, which is measured per batch. In certain formulations, calcium salts may be added to activate low methoxyl pectins. These are metered in precise amounts using microdosing pumps. Water content is balanced by calculating the moisture level of incoming fruit and adjusting with deionized water or fruit juice concentrates. The full formulation, strawberry mass, sugar, pectin, acid, and optional additives, is transferred to a batch vacuum cooker. The cooking vessel is a steam-jacketed stainless steel kettle, often equipped with an anchor agitator and a central high-shear rotor for uniform heat transfer and reduced localized scorching. Cooking parameters are set to evaporate excess moisture, invert part of the sucrose, and activate pectin. The process is performed under partial vacuum to allow boiling at lower temperatures, preserving color and flavor while reducing thermal degradation. Typical target solids content for jam is 65-68 degree brix, measured with inline refractometers. During cooking, water vapor is extracted through a condenser system connected to the vacuum circuit. Condensate is collected and removed via gravity drains or vacuum traps. The jam mass is circulated continuously through the cooker using sanitary centrifugal pumps. This ensures uniform heating and prevents sedimentation of fruit particles. Once the desired brix and viscosity are achieved, the batch is cooled through a scraped surface heat exchanger. This unit has a rotor with fixed blades that continuously remove product from the heat transfer surface, enabling rapid cooling while weighing, preventing fouling. Product temperature is reduced to below 85 degrees Celsius to prepare for filling. Deaeration is performed inline or in a separate vacuum tank. This step removes entrained air bubbles introduced during cooking and agitation. Vacuum is maintained at approximately 0.8 bar, while slow agitation is applied to stabilize the product's density and texture. Optional flavoring agents or color corrections are added at this stage. Natural strawberry flavors or concentrated fruit essences are introduced through metering systems. Any added color is dispersed into a small portion of jam and blended thoroughly to prevent streaking. The final mixture is homogenized using low shear mixers to avoid foam generation. Finished jam is held in surge tanks equipped with level sensors, slow speed agitators, and thermal jackets to maintain flowability. Surge tanks are connected to the filling system via positive displacement pumps or rotary lobe pumps that handle viscous products with suspended solids. Glass jars or plastic containers are depalletized and transferred to the filling line using timing screws and indexing star wheels. Containers are first rinsed with filtered air or ionized air jets. Jars are checked by vision systems for cleanliness and structural integrity. Jam is filled hot, usually between 80-85 degrees Celsius, to enable vacuum sealing after capping. Filling is performed using piston fillers or mass flow-based servo systems. Fill volume is precisely controlled to match container dimensions and headspace requirements. Foaming is minimized by diving nozzles that dispense product near the base of the container. Immediately after filling, containers pass through a capping station. Metal twist-off caps with vacuum buttons or plastic snap-on lids are applied by mechanical torque heads. For metal closures, steam injection may be used just before capping to displace air and create a vacuum as the container cools. Capped jars move through an inverted holding tunnel or a rotary cooling system. Cooling is carried out using ambient air or chilled water sprays to bring the product below 40 degrees Celsius. Gradual cooling prevents thermal shock to containers and promotes vacuum formation in sealed jars. Vacuum level is verified through cap button testing. Non-vacuum jars are automatically rejected. Labeling follows cooling. Jars are dried using air knives or infrared heaters before entering the labeler. Labels are applied using pressure-sensitive or hot melt glue systems, depending on the label substrate and application speed. Coded information such as production date, expiration, and batch number is printed using thermal inkjet or laser coders. Print location and clarity are verified by high-speed vision systems. Jars failing print quality checks are removed from the line. Label jars are grouped into cartons using robotic pick-and-place arms or mechanical collators. Cartons are formed from flat blanks, glued, and sealed using flap folders and glue guns. Carton integrity is checked by sensors measuring weight and dimensions. Cases are packed into shipping boxes or trays. Box formers erect corrugated cases, which are filled and sealed on a continuous motion line. Finished cases are conveyed to an automated palletizer, which stacks them in configured patterns for optimal stability. Pallets are conveyed to a stretch wrapping system where film is applied under tension. Each pallet is labeled with a scannable ID, linked to batch and traceability data. Wrapped pallets are moved to staging zones for distribution or temperature-controlled storage. Throughout the process, control systems monitor and log all variables. Programmable logic controllers manage dosing, cooking, filling, and packaging operations. Sensors measure temperature, flow, pressure, and viscosity. Human-machine interfaces provide operators with real-time control and alarms. Brix levels are verified at multiple points using digital inline refractometers. pH is measured with inline glass electrode probes. Final jam consistency is evaluated using rotational viscometers or Bostwick consistometers. Water activity meters confirm product stability.